Let's work through the BC review. This is Taylor Series Practice FRQs, Worksheet 2. Number 1 here, the Maclaurin series for natural log of 1 over 1 minus x is provided by this power series given by x to the n over n with interval of convergence from negative 1 to 1. Part A says find the Maclaurin series for natural log of 1 plus 3x and determine the interval of convergence. So we're going to use this information to help us create the Maclaurin series for natural log of 1 over 1 plus 3x. We know this natural log function can be is created with this power series, and we see the relationship here is that we see this x here will match up with this x over here. So we should be able to find, so if we can set this to be similar with this kind of a parent function, then we can use this to help us decide what changes needs to be made to create this Maclaurin series. So what we can do is we know that we can rewrite natural log of 1 over 1 plus 3x in this form. So I'm going to have a minus here to match that form, but if I have the minus here, I have to make sure I counter that with another negative so I don't change the value of this expression. So natural log of 1 over 1 minus negative 3x. So now this negative 3x can represent this x, can represent this x here. So I can say that we have the parent graph here with x to the n over n. Then that means the natural log of 1 over 1 minus negative 3x can be, we can then make the adjustment with this power series, and rather than x to the n, it'll be negative 3x raised quantity raised to the nth power, okay, over n. So now if we have this power series, and therefore interval convergence for the original is between negative 1 and 1, so therefore the new interval convergence must be between negative 1 and less than or equal to negative 3x is less than 1. Okay, so then if we have this form here, and if we're trying to solve for x, we can divide every term by negative 3. However, if we divide everything by negative value in inequality, we have to change the signs of those inequalities. So then this becomes less than or equal to, and this becomes less than as well. Or I can say 1/3 is alright, so if I change the inequality signs here, if I divide by negative 3, the inequality, both of them changes, which essentially is the same thing as negative 1/3 is less than x is less than or equal to 1/3. Okay. Part B, find the value of the summation of negative 1 to the n over n. So we see that this is in the form of this given power series. So if I'm trying to backtrack from here back to the original function, then if this represents the x value, then if I plug this negative 1 in for this x, because we know these are the same, and we see these matching up nicely, so if we go backwards, that just means that negative 1 gets plugged in for the x, which is essentially going to turn out to be natural log of 1 over 1 minus negative x. Or 1 minus negative 1, sorry. And then 1 minus negative 1, which is be 1 plus 1, which is 1/2, which is then equal to natural log of 1/2. So all we're doing here is we're just looking at the pattern that's given to us, and we're trying to see how the patterns match up, and see if we can use those patterns to help us solve the given problem. Okay, part C. Give a value of p such that this series converges, but then this series diverge. Give reasons why your value of p is correct. All right, so if we look at this series here, we can see that this series is going to converge as long as this p-value is greater than 0, because the restriction for this is not going to be as stringent as otherwise, because this is an alternating series that converges. So as long as all it takes for alternating series to converge is that the absolute value of the rule of sequence just has to go to 0 as n approaches infinity. Okay, so so as long as the p-value is greater than 0, then we know that this fraction will eventually move its way towards 0. The sequence will eventually go to 0, and that's all that's required by alternating series test. For this, however, we want this to diverge. So if we think about p-series, we know p-series would mean diverges wherever this exponent, this 2p, is less than or equal to 1, right? Less than or equal to 1. So if 2p is less than or equal to 1, then that's the same thing as saying p is less than or equal to 1/2. So we want something that's greater than 0 and less than or equal to 1/2 in order to fulfill both these both scenarios of these series. So then if we pick any p-value between 0 and 1/2 with 1/2 included, then we have a series that we have a p-value that will converge for the first series but then diverge for the second. Okay, part D. Give a value of p such that 1 over n to the p will diverge, but then 1 over n to the 2p will converge. Alright, so if we think about this series, we know that this series will diverge as long as p is less than or equal to 1. Alright, or between 0 and 1. As long as it's between 0 and 1, with 1 included, then we know the series will diverge. Anything alright, less than or equal to 1, but to be more specific, we can say between 0 and 1. Okay, 0 less than or equal to p is less than 1. Okay. Now for the second series to converge, then we need this 2p to be greater than 1. It needs to be it needs to increase at a faster rate than the harmonic series. So 2p is greater than 1 will be where the series converge. So 2p is greater than 1, that means p is greater than 1/2. So if we're trying to find something that meets both requirements, then it'll have to be p is between greater than 1/2 and less than or equal to 1. So p is greater than 1/2 and less than or equal to 1. Okay. All right. Let's look at the second page here. Number 2, we have a Taylor series about x equals 5 for a certain function. F converges to f of x for all x in the interval of convergence. The nth derivative of f at x equals 5 is given by this formula here, and f of 5 equals 1/2. So part A says write the third degree Taylor polynomial for f about x equals 5. So what we can do is we can build our Taylor polynomial by listing out all the necessary information. So we know that f of 5 is 1/2. We know f prime of 5 just means that we're going to plug 1 in for n, and if we do that, we get 1 over 2 times 3, which is negative 1/6. If we want to evaluate the second derivative at 5, it'll be plug 2 in for all the n values, and we get 1/8. The third derivative evaluated at 5, just plug 3 in for all the n's, and we get negative 6 over 40. Okay. So we now have enough information to create our third degree Taylor polynomial. So the first two terms is just going to be a linear equation for slope of the tangent line. So there'll just be y sub 1, in this case will be 1/2, and then we attach the next step is the slope, which is negative 1/6 times x minus x sub 1, which in this case is 5. Okay, and then we can build our pattern. Our pattern is going to be the second derivative evaluated at 5 over 2 factorial times x minus 5 squared, and the fourth term is going to be the third derivative evaluated at 5 over 3 factorial times x minus 5 cubed. and then we can replace second derivative at 5 with 1/8, and 1/8 divided by 2 would be 1/16, and then negative 6 over 40 divided by 6, which is same thing as 3 factorial, will give us negative 1 over 40. So here we have our Taylor polynomial in the third degree. So part B says find the radius of convergence. So radius convergence, we can go through interval. We can find that using ratio test. So ratio test is a sub n plus 1 over a sub n, limit as n approaches infinity, and look to see where this expression will be less than 1. Now we have to be a little bit careful here because this is only a portion of a sub n. Okay, so a sub n is actually going to be this term divided by n factorial times x minus 5 raised to the n. So this entire thing is a sub n. So all we see here is just a portion of a sub n, which is f of nth degree of nth derivative of 5. So what we do is we're going to replace f of n of 5 with this expression. So all this gets plugged in for the numerator here. And if we clean this up slightly here, we see the n factorial cancels out, and then we're left with negative 1 to the n over 2 to the n times n plus 2 times x minus 5 to the n. So this is my a sub n. Okay, so now we're ready for the ratio test. So the ratio test says a sub n plus 1. So I'm going to replace every n with n plus 1. I don't have to worry about the alternator because this is inside absolute value, so I'm just going to just ignore that. So x minus 5 to the n plus 1 over 2 to the n plus 1 over n plus 1 plus 2. So this expression represents my a sub n plus 1 divided by a sub n. Divided by a sub n is the same thing as multiplying by the reciprocal of the a sub n. So the reciprocal of a sub n is just 2 to the n times n plus 2 divided by x minus 5 to the n. Now if we clean this up here, we're going to see x minus 5 to the n will cancel out, leaving me with just one factor of x minus 5. 2 to the n and 2 to the n plus 1 will cancel out, leaving me with just one factor of 2. And then n plus 1 plus 2 is n plus 3 times n plus 2. So now I have something that looks like this. Now if we're evaluating the limit as n approaches infinity, we see that these n values will have the same degree. So the coefficient is also 1, so we can simply cancel those out, leaving me with just absolute value of x minus 5 over 2 is less than 1. If I multiply the 2 over, I get absolute value of x minus 5 is less than 2. Now we're not looking for the interval of convergence, we're only looking to find the radius of convergence because that's what part B is asking for, find the radius of convergence. So once we have it in the form of absolute value of x minus c is less than r, the 5 represents the center and 2 is the radius, so the radius convergence is simply going to be 2. Now if we were to go a little bit further to find the interval of convergence, then we would put x minus 5 between negative 2 and 2, add 5 to both sides, and we get x between 3 and 7. And then we would still have to test the endpoints. But in this case, radius convergence of 2 is going to be sufficient for the answer. All right, part C. Show that the 6th degree Taylor polynomial for f about x equals 5 approximates f prime of 6 with error less than 1 over 1,000. All right, so let's go through this a little bit here. Now, since the series is this is a converging alternating series, right? Every term is changing signs. So all that needs to happen to find the error or the remainder is all we need to do is look at the first unused term. The first unused term is going to be the maximum error for that polynomial approximation. So the first unused term to approximate the 6th degree Taylor polynomial will be using the next degree up, which is n equals 7. So what that means is I can plug 7 into my rule of sequence, okay, and then that will tell me the next, that will then represent the next unused term, which will represent the approximation for that polynomial. Okay, so if I plug in 7 into all the n values, we see the n factorial will cancel out. So that leaves me with 2 to the n times n plus 2, or 2 to the 7 times 7 plus 2, and that's the maximum error. So 27 times um, uh, uh, 2 to the 7th times 9. Sorry, 2 to the 7th times 9, not 27. This is an exponent here. Okay, 2 raised to the 7th times 9 will give us 1 over 1152. And 1 over 1152 is less than 1,000, so that tells us that we are creating, we have a polynomial approximation that is no more than 1 over 1,000 off from the exact, because we see the maximum error is less than that, 1 over 1152. So the big idea here is that the polynomial, the 6-degree Taylor polynomial, is off is off by no more than 1 over 1152 compared to the original function evaluated at 6.